Okay, they may be coming on. Let me just check. I've done this before. I started the wrong Zoom meeting, but let me just make sure I did not do that. Stellar astrophysics. Looks like I got the right one. Okay. So, for those of you who are watching this video later, which is going to be maybe two of you, maybe one of you, great day, keynote address right after school, right after class today is an astronomer, Adam Frank. Be sure to see it. Okay, today's astronomy picture of the day. It is a digitally enhanced and manipulated view of the sky around the North Celestial Pole. The North Celestial Pole, you may know, is the axis about which the Earth rotates, and the sky seems to rotate around the Earth. And it has two poles, the projection of the Earth's north and south pole into space. And there happens to be in the northern hemisphere a very bright star near the North Celestial Pole, which is very useful for navigating and finding your latitude and finding which direction is north, because it always stays there. The whole sky seems to rotate around this very bright star, whose name is Polaris. Why? Because it's at the pole. Interesting facts about that is that Polaris, very useful for what we're talking about in class recently, is a Cepheid variable star. It pulsates on a several-day time scale and changes by several percent in luminosity. So that's exciting. This particular image, they have gotten rid of most of the fainter stars, and they have brought out the contrast of the dust that they've discovered and mapped from some, I don't even remember, the Integrated Flux Nebula. So there you go. So that's fun. The other thing is that Polaris hasn't always been and won't always be at the pole. It happens to be, we live in a lucky time in civilization for that to be happening, because the Earth's rotation axis actually precesses by 23.5 degrees radius, meaning it's 47 degrees difference at the opposite side of the precessional wobble, which happens every 27, 26, 24, 25,000 years or so. Does this sort of profession. And there was a time when Vega was, in fact, very close to, which is one of the brightest stars in the sky, and is the 0 point of the magnitude scale, as you know, and a very important star. The precessional path of the North Celestial Pole takes it right by Vega too. So in several thousand years, I don't know when, but sometime in the next 26,000 years, Vega will be the Polaris of the time. Anyway, that's exciting. What else? Update? Sure. This is, one of them is wagging their tail. Oh, we got a big puppy stretch. That was nice. That was probably feta. Let's see. I can point them out to you. The two light colored ones here are mozzarella and feta. I think that's mozzarella. This is definitely feta. Mozzarella has a little white streak going down her nose. You've got the three black ones, Roquefort, Stilton, and Gorgonzola. I can't tell which is which. And then you got the two medium-sized ones, medium-colored ones are Goat and Havarti. Again, Havarti's more wrinkly than Goat, but I can't really tell. I'm guessing that's Havarti, but I could be wrong. That's fine. It was bath night last night. They're completely adorable and completely out of control now. So we had them enclosed in this little cage container most of the time. But to give them, we have to clean that out once a day because it just gets full of literal crap. And for like 20 minutes, they just get to run around the whole house. And it's complete pandemonium in the most joyful way you've ever seen as they get into all kinds of mischief and trouble. It's adorable. So Right. We'll try to find a time when you can meet them all. And we're still working on that. Excellent. Okay. Enough of update. Where were we? We were talking about supernovae, and we had gone in a couple different directions. This isn't actually the one I want. Oops, that was the one I wanted. I just closed it. Nope, that's not the one either. What? Sure, there we go. All right, this was one of the last ones we saw. So, we mentioned this before, but let me write down some cool facts about the most famous supernova to go off in the last 50 years. Supernova 1997? 1987. By the way, we're going to name these things. Supernova 1987A was, you guessed it, the first supernova to have been detected in the year 1987. Where was I in 1987? I was probably 13. I think I was in middle school. I sort of remember being at a swim meet and having some teachers talking about this. Like, it was a big deal in 1987 for middle schoolers, right? It was kind of that big a deal at the time when it went on. It is the only local supernova of the modern era. And by the modern era, I mean of the past 300 years. It's the only one that's gone off in our galactic neighborhood. It wasn't even in the Milky Way. It was in the Large Magellanic Cloud. And this is the light curve from supernova 1987A. So several things to note here. One is it still the only supernova for whom we had made measurements of the star before it went supernova. We had taken the spectrum of it. We had classified it. We know what type of star it was. I still don't think that's ever happened again. And I'm guessing this is the pre-explosion magnitude because we had that. We knew what this star was about. And so you can see this was a bright star in the Large Magellanic Cloud, as we expect it would be, but still well below even small telescope observation limits to be able to detect. And then over the course of, a day or two, it becomes one of the brighter objects in the southern sky, reaching magnitude like 3 or so. Very visible in the southern. The LMC isn't visible from Geneseo. You had to be in the southern hemisphere to see this thing. I wasn't in the southern hemisphere in middle school. Still have never been to the southern hemisphere. I didn't see this, but this is the typical light curve that we saw of a type 2 supernova, right? And interestingly, we've got some things color-coded here for what is the dominant source of luminosity during that epoch, right? And so the expanding photosphere is the first thing. It's just physically getting bigger, and you get luminosity 4 pi r squared, 2 to the fourth. The thing's getting brighter and brighter. Recombination wave, this is the details of what happens when supernovas, shock waves interact with one another and generate lots of energy. But interestingly, after the first several days, the dominant source of luminosity for these supernovae tend to be radioactive elements decaying. And this first one is radioactive cobalt-56, which again, these elements are generated in large quantities by the supernova itself, and they're radioactive. So over the course of the next several months, these radioactive elements decay into the thing that they're going to decay into and emit all sorts of other energetic particles. And that's the dominant source of luminosity for the next few months. Specifically, cobalt-56 decaying into iron 56. I guess cobalt 56 has a half-life of about 77 days or something. So you expect it to be half as bright in 77 days and another half as bright in 77 days. I'm not sure what causes that to turn off. Seems like that should just keep going. What would cause that to turn off? I don't know. Anyway, dust formation, I'm no supernova expert. You know, rate cobalt 57, you've got a longer half-life element here that's giving you some, and then it's so faint, you know, 15 to 20th magnitude range, you start to see some other structures form and other things happen out of the blue. So that's fun.
56, the one that we used to like stew or sterilize things.
I have no idea.
I remember seeing like a picture floating around of like a bar of some radioactive cobalt that says like that has printed on it, drop it, run.
I don't think this would be that. A half-life of 77 days doesn't seem like it's the kind of thing that running would help with.
Like you're not supposed to, it's never supposed to be in the same room as a person. Like
it's possible. It's possible. I don't know. I don't know how we make this on Earth. But it's a good question. So this is the closest supernova since 1604. I'll say closest known supernova. This was the Tycho supernova that Tycho Brahe observed, which was the last Milky Way supernova that we know of having gone off. And we know what its progenitor was, meaning we had measured the star before it went supernova, and sure enough, it was a B3 supergiant, which is a little bit unusual. I mean, we would have been very surprised if this had been a main sequence star, obviously. The fact that it's a supernova is no surprise. The fact that it was a B star is a little surprising. If you remember the evolutionary tracks of high mass stars, we kind of expect them to be moving back and forth on the HR diagram, but conventional wisdom is that they tend to be over here when they go supernova and not way over here when they go supernova, which is where this one was. It's about 10 times fainter than a typical type supernova. And this could be, they think maybe it was just a denser object, and because it happened to be over here when it went supernova and not that one supernova, it just had a hard time, the explosion had a hard time propagating outward because the star hadn't already been inflated to very large radii. So that could be part of it. And there's a homework assignment about this, but neutrinos were detected. It's the first, I think it's the first non-solar astronomical detection of neutrinos by one of these big neutrino detectors.
This is back to 1987.
Yeah. Of astronomical neutrinos. Yeah, and I think I varied this number in the problem, but I think the actual number that they found was 12 at Super K in Japan, Super Kamiokande. And they had found another 8 at the IMB Cherenkov detector in Ohio. Anyway, it doesn't really matter the numbers, but it's cool that they saw this in multiple places.
The problem mentions that they detected the neutrinos before light. How is that possible?
Yeah, so it's about 3 hours, I think, before they arrived about, this is the next one. They arrived about 3 hours before the light started before arrival of photons, let's say. And it has to do with the neutrinos themselves, right? So here is the center of a supernova. The core collapses, all of these neutrinos are generated, and most of them come flying out immediately because they interact so weakly with matter, they can fly right out. Whereas the shock, in order for the light to get out, that shock wave has to propagate all the way to the outside of the star, and that star has to physically start getting bigger and radiating more energy or getting hotter. And that takes a few hours for that shock wave to actually physically propagate all the way outwards to the outside of the star. So these guys can just get out a lot faster, easier than the photons, which have to go through all that material and progress the right way outwards. Yep. So what does this thing look like today? This is cool because we normally can't look at these things and watch them evolve in real time, and we could in this one. Well, this is the star before it went supernova. This is the star after it went supernova. Right? This is, again, this went from it increased this is a factor of 100 in brightness, basically a factor of 10,000 in brightness. And it was a B1 supergiant to start, right? So this is one of the brightest stars in the most luminous stars in the region. And then it increases in brightness by luminosity by a factor of 10,000. So yeah, it gets really bright. This is what it looks like today, interestingly. Weird. You've got a central ring, maybe isn't that surprising, but you've got these two other non-concentric fainter rings surrounding it. Isn't that interesting? What's going on here? This is another picture of it. This is a zoom in on the central ring itself. You've got the brightness of these notches have changed over time as the thing evolved and got older. So what's happening here? We think that a diagram of this star's shape. So if you remember, I showed you a picture of Eta Carina, one of the most massive stars in the Carina Nebula, and it looked like it had these two huge lobes because it was expelling mass at a prodigious rate. Probably the same thing was happening here in the thousands of years before this thing actually went supernova. And so there were probably lobes of material surrounding this thing that had been ejected previously by mass loss events in that star's past. And as the shock wave progresses, not just through the star itself, but through the intergalactic and interstellar medium, it lights up parts of that as it moves, right? And so what does that look like? Well, if this is a hollow thing, it's going to look like the intersection of a sphere that's expanding outwards, and these two lobes is going to be two two circles that are offset from the original. And this is probably, the central ring is probably, there's probably also a debris disk around here, and the shock wave is just lighting up the debris disk as it moves out. So kind of fun to be watching. You can watch these rings, over the years get larger and progress and get fainter and change in morphology as the thing goes on. So.
Yes, are you still seeing the shock wave from the supernova still going?
That's a good question. I haven't seen anything about this in many years, so maybe not. But I honestly don't know. If we looked at it right now, like this is probably in the 4 or 5 years.
In this picture, is that what we're seeing? Is that's still the shock wave from the supernova?
Yeah. Oh yeah. Oh yeah. Oh yeah.
It's weird that doesn't I don't know, the shock wave would dissipate, I guess, faster than that?
Yeah, I mean it does, but there's still so much energy involved in that supernova that it can, it goes for a long time, even as it goes down as it has to as a 1 over r squared law, because you're spreading that energy over a surface area as it expands. But there's so much energy to start with, 10 to the 45 joules or so that, you can have this thing progress for a long time and still be lighting stuff up visible from Earth. Okay. All right, this all leads us to our next topic, which is nicely brought into by this Cobalt 56 talk, which is where do the elements come from? If you rewind all the way to t equals 0, or even, no, you can't go all the way back to t equals 0. If you go back to like t equals 10 minutes of the universe has cooled enough that, quarks have bonded into nuclei, and nuclei bonded into atoms, and those atoms have even done some nuclear reactions in the first 3 minutes or so of the universe. And then it sort of freezes out at the 3 to 5 minute mark of the universe. And after that, the abundances that are set at the beginning of the universe. And that is roughly entirely hydrogen and helium. So hydrogen, helium, and trace amounts of other stuff. Created a Big Bang. And this is actually, I'm not going to go into the story, but it's a cool calculation to do. And it has to do with what the density was in the early part of the universe and how many photons to baryons there were. And that ratio sets the neutron to proton ratio. And that neutron to proton ratio basically sets the relative abundance of hydrogen and helium in the early universe. And it turns out that pretty much every neutron that's created in that early universe, which does not decay because neutrons have a half-life of about 11 minutes. And so in the first 3 minutes, a substantial number of them go away. All of them get caught up in helium. And so there's way more protons than neutrons, but all the neutrons basically get caught up in helium nuclei, and all the protons are just left with no partner to dance with, and are left as bare hydrogen atoms. And that's it. You've got hydrogen and helium. And there's trace amounts of other stuff. You've got a little bit of lithium, a little bit of boron, a little bit of beryllium that then decays into lithium, but it's still, many, many orders of magnitude below what you've got for the hydrogen. And that's it. There's nothing heavier than that. So where did all of the other elements come from? And specifically, why does, not just where were they produced, but why are they produced in this particular way? This is the relative abundance of elements on the surface of the sun. Relative to scale relative to hydrogen, where hydrogen is set to 12. You may remember when we were doing our other abundance numbers, I said, and we're going to arbitrarily set hydrogen to be 12. We're going to arbitrarily set 12 to all of these. Why? No particular reason, other than it makes all of these numbers sort of between 0 and 12, which is nice. That's really all it is. So, some interesting things. So this is obviously atomic number. We're going up the period, down the period, right and down on the periodic table. This is a log abundance scale, right? This may look like there's small differences here, but this is an order of magnitude. These are actually big differences in the abundances that we go. So hydrogen, helium, clearly the dominant marker still, that's not surprising. Lithium, beryllium, and boron really low. And then you've got some interesting trends, right? It seems clearly like we're getting lower abundance as we go towards more massive elements. You've got some interesting effect where an odd-even effect, all the odd-numbered elements are lower than all the even-numbered elements. You've got this peak here, iron, called the iron peak, where those elements are just a little bit more abundant than you would expect them to be, given the general trend of how this thing is going. And then you've got, sort of order breaking down and things getting weird out here in the higher elements. But where did those come from? And why is it that some are higher than others? And where are they? And why? And this doesn't even get to the isotope interesting isotope information and why some isotopes are more common than other isotopes of certain elements. We can answer that question. So let's go ahead and try. So I'll first write down some of the trends that I just discussed. Solar abundance shows interesting trends. Among them, general decreasing abundance, from carbon to titanium. I'm looking just at this one, the titanium, that's 22. Carbon is, I'm going to give the Z numbers here, 6, 22. Even numbered elements higher than odd. There's a peak near iron, which are called the iron peak elements. You'll hear astronomers use that term. We're talking about chromium and nickel and cobalt and zinc and those things, in addition to iron, chromium, iron, nickel, etc. And decreasing beyond that again. But also kind of a general trend that the evens are on. Okay, so where do these, we need some production mechanisms. These have all been created since the universe froze out of existence. How? Why are we making these elements? There is perhaps the most famous astronomical paper that's ever been written about this topic, and it was written in 1957. And here it is, The Synthesis of Elements in Stars by Burbidge, Fowler, and Hoyle. Astronomers just call this paper B2FH, or B squared FH. It's that iconic. When you can just call a paper by its initials, you've reached iconic status. And this coined a lot of terminology that we still use when we talk about where these elements come from. And basically, you know, it would have been impressive if they had gone and figured out one of these mechanisms. And they basically found 4 or 5 different mechanisms and tied them to every single element that exists and figured it all out and put it all on one paper. It was pretty remarkable and amazing. So, and they got some Shakespeare quotes in there at the start of which doesn't normally happen. They knew that this is a big deal at the time. That's exciting. So, 1957, Burbidge, Fowler, Hoyle. I think Margaret and Jean Burbidge were husband and wife. B squared FH, as it's been known, perhaps the most famous astrophysics paper ever, laid out the framework of processes and importance for each. I'll say relative importance. So here's the basic problem. High Z elements, it's very hard to use protons to add to the mass, right? Once you have an iron atom, it's going to be very hard to smash it with another proton to build up its mass, to build up its Z number, because the Coulomb barrier becomes just too intense. This iron 56 has 26 protons in it. It's a tremendous Coulomb barrier. So if you're going to get things moving fast enough, you're going to be playing the magnetic hockey puck game, and they're never going to be able to hit each other. So protons can't work really once you get past a certain Z number. Basic problem, can't use protons to synthesize heavy elements. The Coulomb force is too high. Coulomb potential kills it. So instead, use neutrons. Neutrons don't have this problem. They can smash headlong into anything they want to that's got charge because they're chargeless. So where are you going to get these neutrons, though? You need an environment that has lots of energy and is very rich in neutrons. Can you think of such an environment? Supernova. Neutrons are streaming out of this thing at extraordinarily high energy and smashing into the things that are falling inward. And you've got a recipe for building up heavier elements simply by smashing into neutrons. Okay, so outgoing stream of neutrons is very energetic. Can react very quickly with heavy nuclei, even if the resulting, okay. So we need to start thinking about isotopes now. Oh, by the way, here is the periodic table and where we think most of these elements came from supernovae to large stars to small stars to those that are only made in labs, or cosmic rays, or the Big Bang. We'll get back to this in a minute. This is a chart of all of the nuclei, of all of the isotopes, right? So you've got Z number on the x-axis, and you've got atomic mass, nucleon number on the y-axis, right? So, helium-4 is going to be 2. Sorry, this is number of photons, this is number of neutrons. So the 1, 1 line is the carbon-12, oxygen-16, helium-4 that has the same number of photons and neutrons. The black, interestingly, is where the stable isotopes are. So interestingly, the stable isotopes go with even number of photons and neutrons for a while, but then the stable isotopes veer up to the top, and the stable isotopes tend to have more neutrons than protons in their nucleus. For some reason that I actually don't know. Got to do with the nuclear physics of how all this all works. If they're not a stable nucleus, this shows you how they're decaying, whether it's an alpha particle or an electron or a positron or some other way exotic thing for those guys up there. So, yeah.
I'm sorry. I was just going to ask, what's the deal with this isotope in the middle, around 65?
This guy?
Yeah, that's fine.
I have no idea. What is that?
No.
This doesn't happen.
Maybe we've never been able to synthesize it? And why would that be if we've been able to synthesize all of these? I don't know.
You could probably get an award if you can fill in that square.
It's probably just,
I think we can do it downstairs. We'll figure it out.
maybe not a Nobel Prize, but you're certainly going to, it's got to be OCD problem for everybody who looks at this chart. That there's, and this is, who knows, it may be already filled in. This is probably a decade old or so. That's not, oh, these are all yellow. Okay, so what happens? If you slam a neutron into an element, let's say you've got an element here, and you slam a bunch of neutrons into it, where is it going to move on the diagram? It moves straight up. You're not changing the number of photons, you're simply adding neutrons to it. Now, normally, you're going to become reach a state where you've got a radioactive element and it's not stable. And usually what happens with an radioactive element is you can't obviously change the total number of nucleons. When you decay, what happens? You're usually changing protons into neutrons and neutrons into protons. That's really the only way decay path you have. Or you're emitting an alpha particle and burning and dying things up. The normal elements down here do that by emitting an electron or a positron and changing one of the states of one of the nucleons inside the nucleus to get it presumably closer to this line. When you do that, you can only move diagonally in this direction on that diagram. That is what happens when you do a data like that. So depending on how fast you can hit this thing with neutrons and how radioactive that new element is and how fast it decays will determine how far it can get up here before it starts moving back down. And then you can hit it with another neutron. And then it will start moving back down. And maybe more neutrons. And in this way, you can build up higher and higher by successively hitting it with neutrons and successively having it decay. This is the diagram that we normally, which is different than the diagram I just showed you. Apologies. So this is usually the way we're thinking about this when we're thinking about these reactions. Now I have Z on the y-axis instead of the x-axis, so it's exactly the opposite of what we had before. And this, instead of being, no, this has to be exactly the same thing I just spoke of. As you add neutrons, yeah, this is number of protons, this is number of neutrons. So I've taken the same graph, I've just converted the axis, and now we're moving this way, and then back up into the left. And then you can head with another neutron and decay another neutron. We just changed the axes, so it's moving in a slightly different direction. That's a way to synthesize heavy elements. So table of isotopes, at least one that has, like I've drawn it here, x-axis, number of neutrons, y-axis, number of protons, neutron capture we move to the right, which won't actually change the element that you're talking about, right? All of these rows are different isotopes of the same element because the number of protons. Z sets the element that you're talking about. And then you have an inverse beta decay. Depending on how radioactive this element is, this can happen fairly quickly. Remember, inverse beta decay, neutron goes to proton plus electron plus inverse electron neutrino. So these are neutrons being turned into proton by an inverse beta decay. That's move up into the left. Move up and to left. Right? Yeah. Oh, thank you. Just to give you an example of one of these inverse beta decays for an actual element, you might have cesium, and I'm going to put both of them here because I don't know what the atomic number of cesium is off the top of my head. It's 55 to 137. Will inverse beta decay into barium, 56, 137. These have to have the same atomic mass because we're not changing the number of nucleons in the nucleus. We're just converting one of these neutrons into a proton, right? Plus electron plus. So whatever you're doing, you're going to keep this number the same, and you're going to increase this number by 1. That is an inverse beta. And you're going to spit out an electron to conserve charge and lepton. This is called, this is called the R process. Because this happens rapidly. This has to happen rapidly. You have to be hitting this thing with large numbers of neutrons before they have a chance to decay, so that you can move it to the right, have an inverse beta decay, move it to the right, inverse beta decay, move it to the right, inverse beta decay. Maybe 2 inverse beta decays. The path will depend on how fast you're hitting with neutrons and how fast these things will naturally decay on them. Yeah.
So would it be like cesium plus a neutron?
Say it again?
Would it be like cesium plus a neutron on the left side, or is that just?
Well, so this is just the inverse beta decay part. This would be cesium, 55, 136 plus neutron goes to cesium 55, 137, right? That's the neutron capture. You're just increasing the number of neutrons and increasing the atomic mass. Does that make sense? And then that's the move to the right. And then the inverse beta decay would be something like this. So both of those things are happening very, very quickly. But some elements can't be made this way. Some elements, some isotopes that we see in nature cannot be made this way physically. Why is that? So here are just examples of the half-lives of some of these elements and how. So here are stable elements, and here are elements that have increasing short half-lives. And so, yeah, you can sort of see the island of stability, and as you move down here, how they become more and more unstable, usually as you move away from the stable line. But let's think about this. What about this element? Let's think about so let's say that right. If I've got so these red isotopes are stable. If you have stable isotopes, or even isotopes whose half-lives are stable enough, many days, many weeks, many months, many years, then you shield certain elements from being created in this way, right? It's easy to make this element. You can just do neutron capture, but you can't make you're only going to move in this direction quickly in the R process. This element will never, in that time scale, decay to this element. And in fact, I'm guessing these are actually stable ones that will never decay. You're just never going to go from there to there by beta. You can't make this isotope by the R process, by building up with neutrons and then having an inverse beta. And if this is a right. But could you add a neutron here? This used to make sense to me. Right. I think anyway, the S onlys are clearly the ones that are shielded by these stable R process elements, right? Especially this one is a very highly, let's say, unstable one, or yeah. Anyway, there are certain elements that act as a shield, and you can't move any further in one direction because they're stable, and you just can't beta decay from them. Right. Right. So let's do this example. We got cadmium here. You hit it with a neutron. This is a stable isotope. Hit it with a neutron. This is a stable isotope. Hit it with a neutron. This is a stable isotope. Hit it with a neutron. This is a stable isotope. Hit another neutron. This is the unstable isotope. It's going to beta decay. This is a fairly stable isotope. You can hit it with a neutron. It beta decays, and now you got a whole bunch more stable nuclei that you can build up. Right. So you can't make these from the R process because these guys won't beta decay unless you start with things that are not occurring naturally in nature anyway that are further to the left. I think that's the basic idea.
Don't beta decay or just having very long.
Or just have a very long half-life. That's right. Much longer than the, by stable I mean very long half-life or infinite half-life.
So then we didn't have very many. There was like we only saw like one hole in that isotope table earlier. So then would the other elements just be just the result of?
Well, this is naturally occurring, right? We can make, and we look at this chart. We can in a lab make all of these by manipulating the scenarios enough to be able to do it. But the problem is how to do it in nature. How can the universe do this on its own without conspiring to make that particular isotope?
So this would have a lot more holes in it if we were only including
many more holes. Many more holes. That's right. We don't see most of these isotopes in nature. Most of them are very radioactive. They just don't last very long. Yeah. But we've managed to make them by various tricks. But yeah, the odd thing with the hole in there is we haven't been able to make it even with our various tricks, and I don't know why that would be. It's an interesting case.
So the black ones on here are the ones that like you could add a neutron to, but then they're not gonna.
Right. You're never going to get anything really up here by the R process because it's shielded by all of these things that will never beta. You can only move to the right on this diagram. I got this wrong because we're doing this the opposite way. You only move up on this particular diagram because we're putting this backwards. You can't move to the right by neutron. Okay. So that leads us to how you can get to S process elements, which are the result of slower processes. And S is short for slow. Here, beta decay must happen, but with time scale of years usually. So, right. Here, instead of beta decay being the issue, we have to build these up somehow from the protons and then beta decay them in the opposite direction. We just have to move in the opposite direction. So, if you can have these things in a higher energy environment and you can manage to get one with a proton, it will move up. And then you can move, if it's not a stable isotope, you can move down to the right to get regular beta decay, where you're turning a proton into a neutron instead of the opposite. But that is a much more slow process. Hence the S process. For S process, beta decay must occur, which is the opposite of inverse beta decay, where a proton combines with an electron to make a neutron plus a neutrino. Well, actually, it's proton decays into a neutrino plus plus a positron? Yeah, plus a positron. Okay. And so must occur, what did I say, between well, doesn't matter. This can happen in red giants. And especially EGB stars. Okay, cool. Right. So we've got the entire list of basically isotopes that we actually see in nature, which are stable, and how you can, in the paths for how you can get there. And I think this is sort of the limit of what even can be made before, you know, the nucleus just doesn't even work anymore to hold it together at all. Usually you've got this N82 here, you've got these two regions where you can suddenly make much more, where you can much harder to make high neutron rich isotopes. Yeah. So that's fun. Okay. Cool. All right, where are we at? Oh, crap, I'm 5 minutes over. You guys need to stop me. All right, sorry. We'll come back and next time start talking about degenerate remnants of stars like white dwarfs and things.
So the rapid process that's happens while you're being rapidly bombarded with neutrons.
Yes.
What's the S? What's
Yeah,
the S?
like
Yeah, the S process is you know these the S process is, I think I missed it's still neutron capture.
Yeah.
But it's neutron capture and then beta decay that happens on years to tens of years time scales as opposed to millisecond, nanosecond time.
So like S process would be like one neutron capture and then a beta decay, whereas S process is multiple neutron captures.
Exactly. And if you've got, let's say let's say this element has half-life of 10 years, right? You can't get to this with a supernova because it's just no way that any of them will decay in that time. But you can get to it if you're adding neutrons slowly.
So it's kind of the same thing happening in each.
It's the same thing in this book. It's the same thing happening in each. One has to be happening on a very fast time scale based on the beta decay rates of these guys, and the other one has to be happening on a very slow time scale to get to that. To get to here, you know, you have to do our process.
And so that's why with supernova, you're only working with your gravity time scale. Only the ones that decay fast.
Exactly. The only beta decays that can happen, inverse beta decays that can happen are the ones where the half-life is seconds, you know, minutes or less, hours or less.
And that's just because supernova happens so quickly.
Because the whole thing is over in you know a matter of days.
So they're just getting like bombarded by neutrons.
Yeah, right. That's right. And so you'll build up heavier and heavier elements until you reach an isotope that decays very quickly. It will decay. But if this element, say, has a 1 year half-life, there's no way to get to that element with the R process.
You need more time.
You need more time. You need to make this element in an environment where it can decay eventually and not get it bombarded with another proton, with another neutron before it decays. That's right.
So this one could like form in like a star, a stable star, but not a supernova.
That's right. So this is where, you've got these red giants, and right. Then my next thing is where the neutrons come from, and there's processes that can create in the surfaces of these asymptotic giant branch stars, even bare neutrons that can then interact with some of these guys on much longer time scales.
Right. Since we're doing fusion, of course, the fission is further out. So, right.
This is still fusion, but it's it's not fusion like we've talked about because you're just smashing neutrons.
Right. The fusion process. We talked about that. Don't produce extra neutrons.
That's right. No, you always don't have extra neutrons lying around.
My only exposure to neutron-based processes has been fission processes.
Yeah.
Okay.
So carbon 12 plus helium 4, for instance, gives you oxygen 16.
The colloquium, you can just find on the physics.
Yeah. No, it's not a physics colloquium. Go to the Great Day webpage.
All right.
It's the Great Day keynote address. So go to the Great Day website, and there should be a link. Should be able to log in.
Okay. Thank you.
Go check it out. Yep.